Hello, I'm Karlo Jukic, and this is Lab 5. So, the introduction, the purpose of this lab is to observe how the forces of gravity and drag affect a stretched slinky in free fall using observed and computational data in terms of drag and tension. Our key ideas here are Newton's second law, drag and tension, and results is that the model is not able to completely predict the motion of the slinky due to problems with oscillation and reserve energy. So our key ideas for this lab is Newton's second law, F equals ma, or F net is equal to change of momentum over time. This is just saying the added up forces in a system add up to its change in momentum or speed. Velocity update, which is how we get our velocity from our collected forces by dividing it by the time, multiplying it by t, and then we get our speed. Position update gets our position out of these averages that we collect in the velocity update. And our drag is the negative magnitude of velocity times the direction of the velocity. So basically, the drag force acts in the opposite direction of the object's motion. So in the tracker, we have our system, which is our slinky, specifically the base. Our surroundings was just Earth and everything else. Our initial conditions, it starts with no initial velocity. Its position is half a meter above the ground, and its tension is the slinky pulling on itself. In this video, the slinky will drop down. The base will hover here while the top compresses down at the bottom, and roughly about at a quarter second, you can see here, it goes into free fall and starts to speed towards the bottom, the floor. For computational model, we can see our initial conditions, which we set our mass to be roughly 0.25 grams or 0.25 kilograms. Our ball position is half a meter above the ground. Delta T is 30 frames per second. Our gravity is 9.8. J hat is positive y direction. Our proportionality constant for the drag is 0.004, since the slinky should be very low. Our first loop, we will have our like kind of phase one, where the slinky sort of hovers in midair as the slinky is pulling on the bottom is getting pulled from the top to stay there, where we have gravity trying to pull the slinky down, and we have tension, which is the slinky pulling on itself going up, counteracting gravity, and F down is just these two gravities added together. We have our update formulas, and then our second phase, we have after the slinky compresses fully, the tension force disappears, and now the gravity fully can act on it, and then drag appears as the slinky actually starts to move. And we have those forces listed there. We have our update formula. And here we can see the results of the computational model, where it falls and it plateaus still roughly at about a quarter second, and then goes into free fall, accelerates downward with a decreasing slope. And here we have our comparison of our computational, our observed, and then combined, where the orange is the computational, the blue is observed. Similarities, we have the same plateau at the start, almost actually exactly at the start, and they fall off at the same time. Our difference is that the observed falls at a faster rate than the computational model, where we can see it has a strong kick of initial velocity at the beginning and falls to the ground much sooner than the computational model. And this observed graph also seems to have a much more linear velocity than the computational. So some sources of error are that we have bad tracker framage on the video, where the actual slinky falling itself has only roughly like 30 frames. So it's not much to go off of, and incorrect modeling while the force is acting on the base of the slinky in the computational model. So there could be other forces acting on the slinky that is not modeled in the computation video. And so our what if question is, what if the model accounted for energy that the spring carries over from the first phase? So in the first phase, as I talked about before, the sling compresses while the base hovers, and then in the transition from the first to the second phase, the slinky starts falling. But what I'm saying is this energy that the slinky has when it's compressing, it over compresses and then will give the base of the slinky a little kick as the slinky overcompresses. It wants to compress back or decompress back to its original form, so the bottom will shoot out faster than it just being pulled down by gravity. So that's what we can see here with our very big kick of velocity at the end. And so our answer is that this probably what accounts for the spike in velocity in the observed data, instead of the steady acceleration down in the computational and that faster time to hit the ground in the observed. The spring gives the bottom a small kick that boosts it downward when it compresses fully, which then shoots it down at a faster speed.